Click the bell icon to get latest videos from Ekeeda.
Hello friends, welcome back to the subject of Machine Design 1. We are right now in the module number 3 where we are learning design of those components which have or which sustain static loads. Static loads which act gradually and they don't change with the time. Anyway, so in the last lecture we have seen the design. Last 3 lectures we are looking at the design of power screw. The power screw we know is a kind of screw that we have learned, right? And that are used for transmission of power. So there are certain aspects that we understand, we learn about their design. This is an example of power screw. Of course, there are many examples of power screw, and in this example, we are going to learn about the screw press. Screw press is an application where power screws are used. So we are going to design a screw press based on the given data. So the topic name itself is design of screw press, power screw. It's a kind of power screw, numerical part 1. This numerical are basically lengthy in nature. Let me recollect it, and that's why we are dividing them into multiple parts. So don't forget to watch the next lecture also, which is based on the continuation of this design. So we are expected to design the first part, which is very important, that's called screw of the screw press, right? So you can go through the images of screw press which are available in your books or which are available on even Google, and you can go through the different components. So they are basically two important components. One is the screw, actual screw, and second is the horizontal section on which or based on which the screw press is made up of. So let us begin with it. So problem statement is very simple, that they have given the problem statement in the simple manner. They have not specified the material as of now. Of course, if the material is specified with the material properties, it's a benefit to us. Otherwise, we have to go for the material selection. So let us go for the difficult step only, that is the material selection onwards and their material properties selection onwards. So the given problem itself says that to lift a load of 30 kilonewton, we have to design a screw press, or to compress a load of 30, so whatever the movement of 30 kilonewton, we need to design a screw press. The extra information they have given is the height of the throat. The throat is something that's called the actual body of the screw press. So height of the throat they have given is 350 millimeter. So in short, the displacement should be 350 millimeter, and for that we need to design the screw press. So let us begin with it. So what are the given data that we will write down? Load, you can say W or P, it's up to us, and that's given is 30 kilonewton. And second thing we have been given is the height of throat, and that is 350 millimeter. That's the only given data. Of course, there is a flexibility in the manner they can provide you the data. Sometimes they will provide you the material also, but in this case they have provided only the two important outputs which are desired, right? So let us start with the material. Now if you go through the PhD data book again, from the topic number 1 itself, you'll get the idea about which are the possible materials we can use for designing power screws or screw press or their bodies or whatever the components associated with. Let's try to learn to select the materials based on the applications, and the thorough information is provided in your PhD 1.9, PhD 1.10. They will find the application. So based on such an application information given in PhD data book, let us select the materials. So I am selecting steel for the screw, steel as the material for the screw, and cast iron as the material for nut. Of course, this selection may differ person to person, but somehow the design aspects and design procedures are same. So let material be For screw, steel, and for nut, cast iron. And hereafter we have to choose certain parameters which are associated with this these materials or these standard components. So the sigma br, let us take, is 8 newton per millimeter square. Now this data is available in PSG data book, so we are selecting it from the PSG that sigma br for the given material is 8 newton per millimeter square. Yeah, and of course the angle psi which is associated with screws, let's say it is h by d mean. Now we'll be dealing with this component separately, but it's a standard empirical relation, so let us use it, and the desired value is 2 for us. Now let us calculate the mean diameter, which is dm. So that's the mean diameter calculation. Now mean diameter is something that is associated with the screw, and for that we need to consider the major and the minor diameter also. So let us begin with it. Generally the expression they have given in the section of power screws is mean diameter should either be greater or equal to the expression of, it's an empirical relation. Some of the empirical relations, of course, we can't by heart them, so we have to refer to the PhD data book for that. So I'm referring to the PhD data book. I'm writing this. It's 2 times the load divided by an expression that says pi times psi into sigma br. So if we substitute the values in this, the values that we have, the load is 30 kilonewton, pi in the standard value of psi into sigma br, which we have considered as 8 newton per mm square. If we calculate this back, we'll get the value of dm equals to, the calculation can be done in separation, so value comes out to be 34.55 millimeter. Now this is a value which is in between, it's a fraction of the value, so let us go for the betterment of this value. So let us round it off. If you again refer to the PhD data book for the power screws, PhD data book, power screws section, you'll find that there is a standard table given for the available values. So referring to the standard table which has a value similar to mean value, that is 34.55, will get, referring to the table, the outer diameter of this screw as 40 millimeter. The inner diameter then comes out to be 33 millimeter, and then diameter associated with the pitch comes out to be 36.5 millimeter. That's called pitch diameter. We already learned certain concepts like pitch diameter, like major diameter, minor diameter, or outer diameter, inner diameter. So this is the pitch diameter associated, and the pitch which is desired for this combination, again from the PhD data book, comes out to be 7 millimeter. Along with which the area of the core diameter comes out to be 962 millimeter square. Now if you say why these aspects are important, when we design a particular power screw application, we need to provide the important dimensions. So these are those important dimensions which are available directly in the PhD data book based on the standard selection, I will say, and which play a major role in actual design practice. So we know this relation that psi is equal to h by d mean. We already know this relation, which is a standard empirical relation, and the value that we have is 2. But right now we have already found out the value of dm. So putting that value, the only unknown, which is h in our case, comes out to be, after calculation, somewhere around 73 mm. So this is a finding for us. Of course, these all are findings for us. The number of threads also are important for the power screw, because it's a screw, and once we know the number of threads, it's easy for us to determine the rest of the aspects. So number of threads. Now again, you can refer to the PhD data book, and the standard empirical relation they have given is, of course, it's logical. Now you must be thinking, what is this relation? It's very easy to remember. It's the number of threads n. H is the height of the screw. So this is the actual height of the screw, and this is the pitch. So the total height divided by pitch, which is the distance between two threads, will give me the number of threads. I already have these values in standard with me, 73 as the H, and the P value is 7. So somewhere it comes out to be 10.4. Now, of course, we know that a number of entity can't be a fraction, so you have to go for the betterment of this, or preferred series for this. So the preferred series which is found for the number of threads can be a sudden next value or can be a standard value. So let us take n is equal to 11. Now this is the possible value of number of threads. So as the possible value of number of threads changes, the value of h will also change. Indirectly, pitch will remain the same. It remains the same because it's a standard value, and hence, again using this relation, I'll find out the actual height, which is supposed to be by n into p. Value of n is 11 and the pitch is 7, and hence the height becomes 77 mm instead of earlier value 73, which was given by the empirical relation. So this is what the possible value of height. No doubt that these all other dimensions will remain same as long as they are safe. So safety also we are going to verify. So this is what the latest finding, h is equal to 77 millimeter. Let's move ahead with finding out the torque. Now there are two ways torque can be calculated in this particular case of power screw, where we have to find out T1 and T2, two different torques, and then we'll go for the combined torque. Of course, the theory of behind this is different, but we are less bothered about it right now because we are more interested in the design procedure, and that's why we are going to look at the step. So next step gives us torque. Now this is the torque which will be acting on the given screw press based on the given input values and the found out design parameters, right? We have to see that whether the screw press which we have selected, the material which we have selected, it's safe to carry this torque or not, and that's why we need to find out the torque first. So the formula is, again you can find this formula in PhD data book, I am referring to that. It says that torque 1 is equal to W times tan of phi plus alpha into d mean divided by 2. The one thing you need to understand that phi here is a helix angle and phi here is your actually angle of friction. But the empirical formula to find out the helix angle is given by tan inverse of, and of course it's a standard practice used all over, where your alpha will be given by the perimeter S and circumference dp. As we put the values, the standard values, will get value of alpha somewhere around 3.493. Now this is of course in degree thing, and based on the coefficient of friction of this material standard, we'll get the value of phi also. So phi value comes out to be, you can skip this calculation because it's a standard value of friction associated with the materials. So it comes out to be 7 degree, which is angle of friction. Now using this 2, I'm going to find out the value of T1, and therefore T1 comes out to be W. The load we already have been given, and I think it is 30. The given data we have is 30 kilonewton. So we're going to use the value again. Let us put everything in Newton term. So 30 into 10 raised to 3 into tan of 2 angles. This addition becomes 10.493 into the mean diameter that we have found out. The mean diameter that we have was 34.55. Sorry, it was 36.5, which we had figured out, divided by 2. So upon calculating this particular stuff, we'll get the value of T1 equals somewhere around 101.404 into 10 raised to 3, and of course the unit, since we are following the basic SI unit, it becomes Newton millimeter. So it's the first form of torque that we have found out. Let us move ahead and find out the next form of torque, T2. Again, empirical formula for T2 says that it is half into your value of 0.25 into your load into 0.8 times mean dia plus 0.4 times mean dia. Again, it's a standard empirical relation. As we substitute these values, half, 0.25, of course it's the coefficient of friction we have, into load that we have to 10 raised to 3. Let me mention that it is mu, coefficient of friction, into 0.8 times of dm that we have, it's 36.5 plus 0.4 times 36.5, and hence upon calculating the value of T2, we will get is somewhere around 164.25 into 10 raised to 3 Newton millimeter. Now upon adding these two torques, we'll get the maximum torque. So we'll say equivalent torque or total torque. If I add this T2 and earlier finding T1, I'll get this value of total torque is equal to 265654 Newton millimeter. So this is what the torque which is going to act on the power screw which is being designed, or basically the screw of the power screw which is being designed. So for this torque, we have to see whether the shear stress that is induced in the body is going to be safe or not. So we know this formula already. Of course, it's based on the shear failure formula, and it says that the tau that can be induced, the shear stress that can be induced, is 16 by pi into the torque, and it is the core diameter cube. We have all these values, so after substituting them we will get 16 by pi into t value that we have found out right now is this, divided by the core diameter we have found out is upon solving this particular relation we'll get the value of tau. Let me solve it for you, and the solved value comes out to be 37.65 Newton per millimeter square. Also, the compressive stress that will act is 35.08 Newton per millimeter square. Now you'll say where this component did come from. This component again is coming from the PhD data book. So from PhD data book, for the specified materials of screw, if you remember, was steel, and for that we are taking this value. Of course, this comes out to be a standard value of compressive stress for this. Now, one thing that you need to understand, like we had already mentioned this in the procedure for power screw design, is the failure per power screw. It's a kind of component is basically controlled by the principal stress theory, where we say that we find out the principal stresses and we compare those principal stresses with the allowable value of stresses, no matter if it is compressive, tensile, buckling, crushing, or you can say the shear stress, right? So after comparing these values, if the principal stresses which are generated in the component are lower than the allowable value, we'll say that they are going to be safe. The same thing we are going to do ahead, and hence let us find out the principal stresses. And hence principal stress is what we are looking at. So we know that the maximum principal stress generally is denoted by sigma 1 will be given by half. Now there are different forms of this formula. Can go for the simplest one, sigma c. Since it's the maximum one, I am considering plus sign, square root of sigma c square plus 4 times tau square. Now using this particular formula we are going to substitute the values which are associated with us. So if I substitute those values, the relation seems like the tau value which we have found out is 37.65, and therefore sigma 1 comes out to be somewhere around 50.43 Newton per millimeter square. So this will be the principal stress that will be induced in this particular application. Now let us consider some factor of safety also. Of course, for the applications like a screw jack, like power screw, or like the one which we are right now designing is somewhere around 3 to 4. So let us say FOS is equal to 3. So based on this, let us let us see whether the safety occurs or not. For cast iron, which we are considering right now, for steel, which we are considering right now, the sigma yield is somewhere around 260 Newton per millimeter square. Guys, we know that it's a ductile material. The steel is a ductile material, and for ductile material we consider the yield stress as the basis of the safety, and that's why allowable value of stress will be sigma y divided by FOS. It somewhere is equal to 260 divided by 3. So the value comes out to be So the sigma allowable for in our case comes out to be 86.4. So this is the allowable value of stress that can be induced, that can be allowed it in the given material. Somehow, according to the principal stress theory, the maximum principal stress that is actually inducing in this body is somewhere 50.43 Newton per millimeter. So we can say that the allowable value of stress is greater than the principal stress, and hence the design is safe in my case. But this is the design that we are considering for based on, or the safety which is considered based on the principal stress. There is another aspect that we need to consider, that is the shear stress. Again, it's a lengthy part, so let us break it down and let us learn it in the next lecture. So in the next lecture we are going to look at the shear part of this and how safe it is, the actual screw is. Fine. So thank you so much for watching this video. If you like this video, please subscribe to Ekeeda. Thank you.